the word at the Drexel email, John, if you want.
Yeah, I just don't want to log into Word on my I just don't want to log into the Drexel environment on my desktop.
Yeah, I feel you.
I'll just go on my laptop.
Hey everyone, welcome back, and let's write some more neat
Alright,
code
first
today.
homework,
So today, let's solve the problem,
basically
merge
done.
strings alternately. We're given two strings, word 1 and word 2, and basically we want to merge them
Very
character by
happy.
character, starting with the first character from word 1, and then adding that
else
to
we
the
got?
output string. So, for example, if we have two words, word 1 is
Week
ABC,
one
and word 2 is PQR. We're going to start with the first character from word 1 and add that to the output, and then we're going to get the first character of word 2, which is P, add that to the output, and then get the next character from word 1, which is B, and the next character from word 2, Q, C here, and then R from this word. And then this is the output string, and that's what we would return, just like we have over here. Now, in this example, both strings were of equal size, but we could run into a case where one of the words is much longer than the other one.
Okay,
So, for example,
this is exciting.
if we got to the point where we
I'm
were
gonna
at
do
this,
all this
where we took
fucking
the first three
homework
characters
right
from
now.
each
Is
string,
that
and then
smart?
we had,
Is it a
and
good
then we run
idea
out
to
of
do all
characters
the
from word
homework?
1, nothing left here, but we have a bunch of characters in word 2. Well,
Day one.
I like that. That's my mindset.
Okay.
What else are you gonna be doing instead? Playing League and jerking off? Yeah.
then in that case, we would just take
I
whatever
was
is over
gonna
here,
say
let's say
playing
XYZ, something, something,
American
and then just
Truck
append that to the
Simulator.
string that we currently have. So we
And
would just have XYZ and whatever else comes
the
over
other
here.
word
So
you said.
algorithmically, the way
Yo,
we're
why
going to code this
ain't
up is
this
just by having a
charging?
pointer for word 1, let's say that's I, and
Hold
have a
on.
pointer for word 2, let's say that's J, and just keep iterating through these while both of them are in bounds. And when one of them goes out of bounds, we take all the characters from the other string and then append that to the result that we had. So overall, the algorithm is going to run in O of n plus m time, because word 1, let's say, has n characters, and word 2 maybe has m characters. We have to visit every single character from each string. So now let's code it up. So I'm going to start with initializing our pointers, I and j. I'm going to set both of them equal to 0. They're going to be at the beginning of each of the words, and we're going to be building our result. And even though the result is going to be a string, appending and updating a string is not an efficient operation. It's more efficient to just add the strings as characters to an array, and then at the end we will join all of the characters in that array like this. In Python, you can use that empty string as the delimiter and basically say all the strings in result are going to be appended together with this in between them, and this is an empty string, so basically nothing in between them. So now let's actually build that output string. Well, first of all, we're going to be iterating while the I pointer is in bounds, while it is in bounds of the first word, and while j is in bounds of the second word. As that's the case, we're going to take whatever character is at index I in word 1 and append that to our result like this. And I'm going to copy and paste this line because that's what we're basically going to do with word 2 as well, except with pointer j. So just like that. And then don't forget to actually update the pointer, so I is going to be incremented by 1, j is also going to be incremented by 1. At the end of this, one of the strings could still have characters left, so in Python, the easiest thing to do here would just be to append to the result. Well, append like this, since result is an array, the substring of word 1 starting at index I going up until the end of the string. So if I is out of bounds, this will append nothing to result, but if I is in bounds, we'll append the remaining characters of word 1. And we're going to do the same thing with word 2, because we don't know which one of them could still have characters left. So with word 2, we're going to use pointer j, and just like that. Wow. And this will ultimately return the result we want, so let's run it to make sure that it works. As you can see, yes it does, and it's pretty efficient. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.
I and j starts at 0, 0. Result is a list because lists can be appended faster, while I is less than the word 1. Word 2. Result dot append word 1 dot I. Oof, that's exciting. I plus equals 1, j plus equals 1. Then after we get outside, we got results dot append the rest of word 1. I, bam. Result dot append word 2 dot j. Holy crap, guys, this is amazing mathematics. Then return it as a string. Oh shit. Join. We want the result. Bam. That's beautiful programming, guys. Very beautiful programming approach. I like that. Good way to learn that one, guys. Let's now go to sliding window. You're given a string S consisting of only uppercase English letters and integer K. Choose up to K. Oh god, what's back? Alright guys, I have no idea how to do this. Let's see what the solution is.
Hey everyone, welcome back, and let's write some more Leetcode today. So today we're going to solve longest repeating character replacement. And so this is another problem from that blind 75 list. So we're going to be one step closer to completing the entire list. The link will be in the description to the spreadsheet if you do want to take a look. And hello to the 6 people that are currently viewing the spreadsheet right now. You're going to be in the next video. But okay, so let's get into this problem because it's another pretty fundamental problem that's really good to understand. So we're given a string s and a single integer k. And so basically they tell us that we can choose any of the characters in the string and change it to any other uppercase English character. So in this problem, every character in the input string is going to be limited to uppercase English characters. And we know that there's 26 uppercase English characters from capital A to capital Z. And so basically we can perform a replacement on any of the characters at most k times. So we're allowed to replace k different characters in the string to any other character we want. And what we want to do is return the length of the longest substring containing the exact same character we can get after performing at most k different replacements. So we just want to return that length. We don't actually have to make those replacements in the input string. So in this case, when we take a look at the input string, we have AB, and we're allowed to replace 2 of the characters. So what's the longest substring we could get with the exact same character? Well, we could replace one of the B's. We could basically replace both of the B's with a capital A, and then we get 4 A's in a row, which would give us an output of 4. And we could technically also do the opposite. We could replace the A's with capital B's, and that would give us the exact same result, a length of 4. So I'm going to show you how you can solve this problem in big O of n time, and technically it's going to be big O of 26 multiplied by n, which we know is also reduces to big O of n. But there's actually technically an easier way to do it, or at least a more simple way to do it, which is just going to be a flat big O of n. We don't even need this 26 constant. But this way is actually pretty tricky to get to, so I'll be going over a little bit of it, but this is kind of the main way that you'd want to solve this problem. So let's say we're given an input string like this, and we're given a k value. Now the most brute force way would just be check every single substring, right? And if we were checking every single substring in the entire input array, we know this stands for substring, so that wouldn't be the most efficient way to do it. But even if we were doing it,
Long time no see, buddy. Your boy is locked in right now, leak coding. I have 4 interviews next week, so I am doing nothing but leak coding. It was nice seeing you again. What you been up to?
like that, what exactly are we looking for? If we're looking at a particular substring, how do we know if this substring is valid? Because remember, at the end of the day, we want to maximize the result, right? The result is going to be the longest substring that contains a single character, and we can make 2 replacements. So let's look at this substring alone. How do we know if it's valid? Well, which character are we going to replace? Are we going to want to replace the B's in order to make it all be to match A, or would we want to replace the A in order to match it with the rest of the B's? Of course, we're going to replace the character that occurs less frequently, right? Because the number of replacements we have is limited, so we would want to replace the characters that are less frequent. So in other words, we want all characters in a particular window to match the most common character in that window. So what we're going to be doing is we are going to have a hash map or a array, which is going to take every single character. In this case, we only have characters A and B, and we're going to count the number of occurrences of each character. So for example, if we were looking at this substring, we see that there's 3 B's and we have a single A. So how do we know if this window is valid? What we're going to do is we're going to take the length of the window, which is going to be 4, right? We're going to take the length of the window, right, which we know in this case is 4, and we're going to take the length or the count of the most frequent character. In this case, we know that that's B, and the count of it happens to be 3, so we're going to take 4 minus 3, and from that, we're going to get a 1. Now, what does this value 1 tell us? It tells us the number of characters in our window right now that we need to replace in order to make it match the most frequent character B, right? We have a B here. We want everything to match a B. In this case, we only have an A, right? But it could be possible, like, who knows, maybe that we would have a C over here, right? Or an X over here. And it doesn't really matter what the characters are. We just know that B is the most frequent character in the window, and the other characters that are not B, A and Z, for example, are the characters we want to replace. So we can calculate the number of characters we want to replace just like this. And so we want to replace 1 character. How do we know if we have enough replacements to do 1 character? Well, of course, that's our input parameter K, right? So what we're confirming here is that this value is less than or equal to K. As long as this condition is true, that means our current window is valid. That means we have enough replacements to make those replacements in our current.
Nice. Been working here on trying to learn QuickShow so I can customize my desktop. Ooh, what are you? Are you use Linux? Yoshi boy, you a Linux user over there?
Window. So this is the main condition that we're going to be checking.
Cool, though.
The other question is, how are we going to know which character is the most frequent? Well, the brute force way is going to be taking a look at our map of counts, and we know that the max size of this could possibly be 26 because we only have 26 different characters. So finding the max character is going to be big O of 26. So that's a little bit more inefficient than we would like, but it's technically still linear time. Like the overall algorithm is still going to be linear time. The last thing that we're going to have to do though is to this equation, we're going to have to add a sliding window technique. So basically what we're going to do is we're going to take our window, start at the beginning, expand it as
Endeavor OS user. I definitely need to move to Nix OS sometime. Oh, that's some niche stuff right there, Yoshi boy. I respect it. This is the difference. That's how you know you're a true software engineer. You got niche interests like that.
The condition that we mentioned is valid. If the condition is not valid, then we're going to take our
someone
left
like
pointer
me. All I can
take
do is just leak code and
as well until the
generic.
string becomes valid once again. So we're going to have a left and right pointer. So initially left is going to be at the beginning and right is also going to be at the beginning. And also the counts of A and B are initially going to be 0. Now we're going to look at the first character, right? That's where our right pointer happens to be. We're going to look at it. We're going to say, okay, we have a single A, right? We're going to take our count of A and set it to 1 now. So is this window valid? As in, can this window be the exact same character within 2 replacements? Of course it can, right? That's kind of the trivial case, but we would still calculate it. And the way we would calculate it is get the size of our window. Right now we can see the size of our window is 1 subtracted by the count of the most frequent character. In this case, we know the most frequent character is A. 1 minus 1 is that less than or equal to K? We know K is 2, so of course this is going to equal 0. 0 is less than or equal to 2, which is K, right? So of course this window is valid. That's kind of a trivial case. Next, we're going to shift our right pointer to the next character, right? So now we have a B, so we're going to increment the count of B in our map. So B is now going to be set to 1. In this case, the length of our window is 2. The most frequent character is either of these, right? And the count of that frequent character is going to be 1. So we're going to have 2 minus 1 equal to 1. So this is the number of replacements that we have to do. And looking at our current window, that makes sense, right? We have to replace
what speed are you watching on? I'm watching at 2x speed right now. If you have YouTube Premium, you can watch at 3x speed, guys. That's the best part. But I'm watching at 2x speed because, listen, I'm just trying to understand it. I'm trying to understand the thought process, guys. See, a lot of people don't realize, people think Leetcoding is just coming up with the best solution. No. Leetcoding is coming up with a solution, and before you come up with the solution, your thought process and analyzing the problem. But listen, guys, everyone knows there's always a... Gotcha. I normally watch 1.75, a little too fast for me. Listen, the trick is you gotta have the captions on. I have no idea what this guy's saying at 2x speed, but with the captions, bam. So I understand generally some of what he's saying.
So we're going to ensure that the number of replacements that we need to do is less than or equal to k, which is 2. Of course, that's true. So our window is currently valid.
Trust me, guys,
you
gotta read the captions.
So since this window is valid, the length of the window is going to be set to the result, right? So right now the result is 2. 2 is the length of the longest window that we can get. So that's our result for now. So now let's...
But I'll be honest, guys. Right now, I'm at the point of Leetcode where I'm just trying to understand what he's thinking, because at this point now it's a little too late for me. I've only got like 4 days to prep. Now, but I just gotta just experience every problem. I gotta see what he's thinking. I gotta see what the most efficient solution is, and that way that thought process is just in my brain. That way, when it comes time to code, hopefully the person that's helping me interview will just help me
continue. Next, we're going to shift our right pointer to the third character. So now we get another a. So we're going to take the count of a and increment it all the way to 2. And we're basically going to repeat our algorithm. So once again, we're going to get the length of the window 3 minus the count of the most frequent character. We see the most frequent character is a, so the count of it is 2. 3 minus 2 is 1. Is that less than or equal to 2, which is k? Yes, of course it is. So this window is also valid. We can update our result now to 3. So we found another window even longer. So I'm going to take our right pointer once again and then shift it over to the b. So now we're going to be, since we reached another b, we're going to increment the count of b to 2 now. And so the length of our window now is 4.
Leetcoding a little bit more,
the most frequent character is either of these, and that's going to be 2. 4 minus 2 is equal to 2. Is that less than or equal to k? K is 2 in this case. So of course, once again, this condition does hold. So once again, we found a window that's longer than our result. We found a window now of length 4. And so once again, we're going to take our right pointer and shift it. So now another b. Let's increment the count of b to 3. So the length of the window now is 5 minus the count of the most frequent character. That character is b. 5 minus 3 is this 2, and less than or equal to k. Of course, it's still true because when you look at our window, we have 3 b's. So that means we're going to be replacing the a's. So we're going to need to make 2 replacements, and we are allowed to make 2 replacements. Okay, so now we're finally going to get to the case that I mentioned earlier, where we're going to take our left pointer and then slide it to the right, which is why this is a sliding window problem. So now we reached an a. So we're going to take the count of a and set it to 3. So now we have a count 3 and b count 3. So let's take the size of our window 6, subtract from it the count of the most frequent character. It's going to be either of these. So 6 minus 3 means we need to make 3 replacements. Is that less than or equal to k? K is 2. So we exceeded k, right? We exceeded the number of replacements we're allowed to make. If we wanted this window to be valid, we have to replace 3 characters in it, but we're not allowed to do that. So what we have to do is shrink the size of our window until we are valid. So we're going to take our left pointer and shift it to the right. So now the left pointer is going to be over here. It's going to be at the b. So since we removed this a from our window, we have to decrement the count of a in our window. So I'm going to cross this 3 out, and now it's actually going to be set to 2. I kind of ran out of room, but I hope this is still readable. So now the count of a is 2. So now let's once again check, is our window valid? Well, the size of the window now is 5, and the count of the most frequent character is b, and that's going to be 3. So 5 minus 3 is going to be equal to 2. Is that less than or equal to k? Yes, we are once again valid. So this is technically a valid window, and I think I forgot to update the result earlier when we had a window of size 5. So the result right now would be size 5 because the longest window we can make is either this window or the window that we had earlier with these first 5 characters. But yeah, and so at this point we would stop our algorithm because we did find a window of 5 that is valid, and our right pointer cannot be shifted anymore. So this is the general algorithm. So it's a fundamental sliding window problem with this particular condition being important. But there's actually one way you can do it without having to look through the entire hash map every time you want to find the most frequent character that occurs. And it's kind of tricky to arrive at the solution, but it's pretty easy to implement once you can figure it out. I'll explain the algorithm at a high level. I don't want to waste too much time on it, but basically we're going to be having another variable, and it's going to be called max frequency, basically the count of the most frequent character at any given time. So basically, for example, if we had a as a count of 3 and b as count 2, we'd say, okay, the count of the most frequent character occurs 3 times, so max f is going to be 3. And so anytime, if we got a b, let's say we incremented our b all the way up to 4, then we want to update our max frequency to 4, right? So we'd always want this to be the most frequent character. Now, the one problem is if we're trying to maintain the count of the most frequent character, what happens when we take our left pointer, for example, right, and then shift it, right? When we do that, we're basically removing a character, and therefore we have to update our count map, right? We are going to do that, and if that does happen, right, let's say we took b, and then from 4, we decremented it all the way down to 2, for example. Then we have to rescan this entire map and then find, okay, what's the new most frequent character, right? So we have to take our max frequency and from 4 downgrade it all the way to a 3, for example. So then we have to set it to a 3, and that would basically defeat the purpose, right? We'd still have to do that big O of 26 calculation to scan through this. But it's technically true that you don't have to decrement this max frequency. But the main idea is this. The result is only going to be maximized as we find a new max frequency, right? Because remember what we were doing. We were taking the length of the window subtracted by the max frequency, right? Whatever the most occurring character was, and we wanted to minimize this, right? So basically we want the length to be maximized because that's what our result is going to be set to. So therefore we also want the max frequency to be maximized because we want to ensure that this is less than or equal to k, and k is going to be a constant. So for example, let's say I had a max frequency of 4, but let's say now the new max frequency got downgraded to a 3. I'm still going to leave this as a 4 because it's not going to change our result. Because for example, if I had a 6 minus 4, that was less than or equal to k, which is 2 in our example. And if I leave this as a 4, I'm basically overestimating what the max frequency is. But we know at least at one given point in time it was a 4, so therefore we were able to take the length 6 and then set it equal to our result. And now, if we're ever, so let's say our result is now 6. If we're ever going to increase the result from 6 to another number, like for example 7, we would require our max frequency to increase. If it stays the same or if it decreases, our result is never going to change because we only change our result when we increase our max frequency, because that's the only way this condition here is going to be true. So if our max frequency is downgraded, we don't have to actually update it. We don't have to look through the entire hash map to find the new max frequency. But if we increase our max frequency, for example, if I took this A and then from 3 I set it equal to a 5, then that's something we can check in big O of one time. And then if we increase this, then we definitely do want to update our max frequency and increase it. And that's something we can do in big O of one time. So I know I probably went a little too long into this, but the main idea here I'm trying to get at is the easy way to solve this problem with a sliding window is going to be big O of 26 times n, which is technically linear.
Oh, great.
There is
I
a
really
clever way
need
to do this
that
in big O of n
textbook.
time that honestly I didn't figure out on my own, and I wouldn't really expect other people to be able to figure it out on their own, like in an interview at all. But I will show this, the standard solution, and I'll also show the code for this more optimized solution. Okay, so now let's jump into the code, and the code is actually a lot easier than the visual example that I gave, a lot shorter for sure. So we're gonna have a hash map to count the occurrences of each character, and we're also gonna have a result, which is gonna tell us the longest
Hash map.
substring that we can create with k replacements, and we're gonna have a left pointer, which is gonna be at 0, and then our right pointer is gonna go through every single position in the entire string s.
You
so
look
what we're
like
gonna
a
do is for the
hash
character
map.
at position r, we're gonna increment the count of it. We're gonna take 1 plus whatever the count currently was, count.get this character, and if the character doesn't exist in our hash map, we're just gonna return a default value of 0. That's what this function is doing. And so before, what we're gonna obviously do is update our result, right? And we want to set the result equal to the max that it's ever been, and set it basically equal to the size of the window. We can get the size of the window, so we're gonna take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm gonna do is basically say while, and I don't think you actually need a while here. You could just do if, but I'm just gonna do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here. So I'm just gonna copy and paste that. The length of the window subtracted by the count of the most frequent character, which can be gotten with max of count dot values. Right? We're basically going through the hash map, which could be size 26, and just getting the max value from it. So this is the number of replacements that we have to do. And if the number of replacements was greater than the number of replacements that's allowed, which is equal to k, that's when we would want to shift our left pointer. So we want to increment our left pointer. But before we increment the left pointer, we want to take the count of the character at the left position and then decrement it by 1. And that is the entire algorithm. After all of that is done, after we've gone through the entire string, then we can just simply return our result. And as you can see, this is pretty efficient. It's linear time. It's about as efficient as you would need, I think. But I'm going to make that slight optimization that I showed you. I'm going to maintain the max frequency in a single variable so that we won't have to do this operation where we're getting the max of the entire hash map. Instead, up here, before we execute that loop, I'm going to say max frequency is going to be equal to the max of what it currently is, max frequency, or it's equal to the frequency of the character that we just added a value to. Maybe that character became the most frequent character. So we would have to update our max frequency, and we can do that just like this. And this is a constant time operation. We're not scanning any list or anything. And then once we have this max frequency, we can use it in this loop execution, right? So we can replace this and just use max f for that. And the thing is, notice how even when we're shifting left, we're incrementing the left pointer, we're potentially removing characters from our window. We're still not decrementing max f because we actually don't need to. It won't end up affecting the result if we just don't decrement it. And that very slight optimization, which is really simple in terms of code, but it's kind of hard to see why we're allowed to do that. And watch how much more efficient it makes our algorithm. So as you can see, look, it definitely improved. I think it was 50 milliseconds difference. So this is significantly
That is a
faster. It's hard to
huge
see
jump.
why though. I would definitely not expect most people to be able to figure that out. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.
Alright guys, well I wouldn't be able to figure it out, but we're still gonna claim that we figured it out. That's me, baby. That is me. So we got a hash map here count, which counts the number of frequencies. The result is equal to 0. The length, which is equal to 0. The left pointer, my fault. Max f, the max frequency for r in range. The length of s, which is the string input. Count sr to increment. Use to increment the right pointer. 1 plus count dot get sr, and it's gonna add it in there if it doesn't exist. The max frequency is the current max frequency, and then count sr. There we go. While r minus l plus 1 minus max frequency k, count sl bam minus equals 1. We have that, and then left pointer plus equals. So this is incrementing the left pointer once we start getting out of bounds. And this is just going to be incrementing the right pointer above it. Then the result is r minus l plus 1. Result, return result. There we go, guys. Bam. Bam. It's gonna keep returning result until it's gonna keep incrementing left pointer until we get inbounds for that. Tough.
Let me get my notebook.
Get your notebook, T Diddler. Get your notebook. What the? Key error. X. Should be an X. It's my key error here. Guys, what the hell? SR equals R plus equals. My fault, guys. Not bad at all. Bam! I feel good about myself, baby. Let's get it. Let's get it, guys. Did a sliding window. Let's go do our stack problem. Implementing a queue using a stack. FIFO! First in, first out. Let's see what I got here.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, implement queue using stacks. If you don't remember what a queue is, it's a first in, first out data structure. So for example, we have a few operations that we can perform. We can push elements into the queue. In this case, they're going to be integers. We can pop elements from the queue, and those are the main operations. We'll quickly go over these two, but just to keep things simple, we're going to focus on
Alright guys, let me get myself a cup of coffee. I'll be right back. I'll be right back, boys. Gang, I am back. Taking some Python notes. Take it, Chibi. Chibi, you are going to be the one to change the world. You are going to be like, oh my god, Sami, because of you, I've 10x'd my career. Thank you for your help. I'll be like, Chibi, all along it was just you. You were the one who helped your career. Trevor's going to be like, software engineers aren't real engineers because they're not engineering certified. Blah, 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 blah. And then I explain to Trevor, well, historically speaking, software engineering is a new field. Blah, 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 blah. Give me 1 second.
Let's get this done.
I am back, gang. I just finished using the bathroom. Yes, get it.
I mean,
Yes, get it. Chibi, you are a boomer for saying yes, get it. Trevor, are you there?
yeah.
I came back just in time. Yeah, I was having a conversation with my brother while I was brewing my coffee. I had to explain to him because like I told him I want to get like the 350-pound like certified grip thing.
Mm-hmm.
So Chibi, cool fact, there's hand grippers. Right now I can squeeze 200 pounds for like 3 reps, but to get more reps I'm doing 150. And once you can squeeze 350, you can get certified for squeezing 350. And he was like, dude, that must hurt. And I was like, why? He's like, because imagine every time you're doing something, you just squeeze it with 350 pounds of force. And I'm like, what? And he's like, dude, once you have that, like, that's your permanent squeeze strength. And then I was like, that doesn't make any sense. You choose the amount of force you push with. He's like, that doesn't make any sense. He's like, how can you do that? I was like, I mean, like, can you push more force into the ground right now with your foot? He's like, yeah. I said, so why can't you do that with your hand? I thought Zoomer started saying Esket. Was it? Esket. What? Did millennials? Lil Pump. Trevor, what era is Lil Pump? Oh, is that Gen Z? Oh,
Yes. What the hell?
Oh,
That was
shit.
like 2017.
Nah, that's more of an older generation thing. They probably still living with Lil Pump. You know what I mean?
Peek is basically just going to return the element at the front, and the other function is just to check if the queue is empty or not. So just to quickly simulate, suppose we do a push. We push 1. Suppose we push again. 2. Push 3. Push 4. Just to be clear, this
Guys,
is
if you
the
hear me
front
grunting,
of
I'm
the
using
queue.
this.
This
I'm
is
using
the
this.
back of the queue. We push to the back. We pop from the front. So now if we were to do a pop operation, we'd want to remove 1. Then we'd want to remove 2, etc.
Data
So when we
structure.
say we want
It's
to
a queue.
keep an element, we are just going to return the element from the front without popping it. Okay, not super complicated, but our job is to actually implement this
Damn.
data structure with
Guys, I
2
broke my
stacks.
mouse and I can't
And
ever
how
use
a
it
stack
again.
is, it's kind of like this, except basically we'll push 1, we push 2, we push 3, we push 4, and then when we remove from the same side. So now we want to pop 4, pop 3, pop 2. We don't pop from the other side. This is called a stack, and it's pretty easy to implement because removing typically from the end of an array isn't very difficult. We can kind of do a soft delete. Like if we were just maintaining an array and we had like, okay, the length of the array right now is 4.
All right,
Therefore,
whatever.
This
This
is
is
where the last
hidden.
element is.
Yeah,
And
we'll
we can delete
just-
this element
we'll
without actually
just-
deleting it. We just take this pointer and shift it. So stacks are pretty easy to implement. I go over this, I think, in my data structures beginners course, a lot more in depth if you're interested. But clearly the problem is in the queue, we remove from the other side that we push from. So removing from an array over here is not as efficient because if we want to remove this, we kind of have to push everything over. So that ends up being a big O of an operation. And if you try to handle it with like the soft delete that I just talked about, you're going to realize that the pointer here, like let's say we deleted all of these, now our pointer's all the way over here. Look at all that unused memory. Again, I go over stuff like this in the algorithms courses, but you don't need to know this super in depth, I think, to solve this problem. So back to the problem, given this type of data structure, 2 stacks, how can we try to solve this problem? And they actually mention in the problem description that it's possible for us to solve this in such a way that we use 2 stacks and the average case time complexity of all of these ends up being constant. And that's actually the hard part of this problem. So first we're going to solve this problem without considering that requirement. Let's just solve this problem using 2 stacks in a naive way. So let's say this is stack 1 and this is stack 2. We can only really push and pop from a stack. So naively, let's say we had this same sequence of values. Let's say first we want to push 1, next we push 2, next we push 3, and let's say we do 4 as well. Now we want to pop. How do we do it? Well, for us to remove an element here, we have to kind of get rid of it, and at least with a normal array, we do that shift thing that I talked about. We shift every element, but they tell us with a stack, we can only use the stack operations, push and pop. So can we accomplish the same thing without doing this, basically without like indexing the stack, because that's not usually allowed with a stack? Yeah, we actually can. How would we do it? Well, it's probably not going to be by pushing an element. You can guess that we probably want to pop, pop, pop until we have the last element remaining. But we don't want to get rid of these, then we lose what we had. Well, that's kind of what the second stack is for, isn't it? So as we pop these elements, we can push them to the other stack in the same order that we're popping them. What happens when we do that? Let's just try it and then see what happens. Okay, we get 4, then get 3, then get 2. Looks like the order of these was actually reversed. So when it comes to coding this up, instead of hard coding it such that we wait until the length of S1 becomes equal to 1 so that we have the last element and then we can pop it, let's just take every single element here, pop it such that it gets pushed to this other stack. So now look at what we have done. We've reversed the order. Why does that help us? Because now when we pop, we're actually popping the correct element. Because remember, this is the sequence. This was the sequence. This is what the real queue would look like. 1, 2, 3, 4. We push here to the back of the queue. We remove from the front of the queue. So far so good. We now are able to pop this element here. But remember, we kind of reversed the order of these. So let's just take all of these, add it back to the first stack in like the same order that we popped them. Well, in the opposite order, I guess, so that we now get 2, 3, 4. So if we were to pop these, this is what we would get. And that's fine because now when we want to push to the stack, we can push in constant time. Just to review, the solution I have shown you, pushing is constant time, and popping, since we're popping from the other side, it's going to take big O of n every time to take all the elements, move them to the other array, and then move them back. That's going to be the bottleneck, popping. But they claim that somehow we can get a solution in constant average time. So tell me, theoretically, how would that even be possible? Well, with 2 stacks, we know we really don't have a lot of options. We can only push or pop. And we already decided stack 1 is where we're going to push. That's constant time. Somehow, if we can make it so that stack 2 is the one that we're always going to pop from, which we kind of already did, that pop itself will be constant time. But the bottleneck was when we had to move all of these elements there and move them back. Do you see something that we could do? We don't know what the next operation is going to be. We don't know whether it's going to be a push or a pop. But if it were to be a pop, wouldn't we want to leave the elements like this? Because we did that operation. We did that big O of n operation. Why do we want to have to do it again? Because it looks like the numbers are already here. If we want to pop again, we could do that actually in constant time. If we want to pop again, we could do that in constant time. Okay, but what if we wanted to push an element? Well, I guess we could still push an element to the first stack. Like, for example, now if I wanted to add 5 to my queue, so I'm going to put the 5 up here in the original queue. And then if I wanted to add 5, I'd probably push it here. We've decided that's where the most efficient place to push is. Now, if I want to pop again, what am I going to do? Because originally, we took all these elements and moved them there. Well, right now, it doesn't look like we need to do that. Again, look at the input sequence. We've removed 1 so far, but the next element we want to remove is 2, and we can do that. It's right here. It doesn't matter that we've added 5 because this second stack, the one that we're going to pop from, is non-empty. So what we can decide is pop from here, and pop from here. If we want to pop again now, well, stack 2 is empty. So let's go look at stack 1. Maybe it's empty too, and we just can't do another pop, but it's not. So now is the part where we would take all these elements and then push them here, just like before. And if it's one element, we do that. Perhaps it would be multiple elements, and we do the same thing. They'd be added here in the opposite order. That's the key, because when we pop from here and then push here, the stack gets inverted. That is the key here. Because remember, push here and pop from here. We can do that because the order is good for what we want to do, and it works. Now, this isn't super complicated, is it? The hard part about this is the fact that we are trying to find a solution that is amortized, or you can think of that as like the average case time complexity. If we do several calls to this queue, we want that to be constant for both.
Amortize!
That is really the hard part about this problem. So let me kind of give you the information of why that is kind of guaranteed. Let's go through a few examples here. The trivial one is if we push, then we pop. We're going to end up popping this and moving here, and then popping it from here. So pushing is obviously going to be constant, and then popping is going to be constant because we're going to move it here and then remove it. So if we just did push, pop, back and forth, it would be fine. What if we instead had a long sequence of push operations, and then we had a pop after that? Well, we kind of showed that earlier. We'd have a 1, 2, 3 here, then we'd invert the order, 3, 2, 1, and then we'd start popping. If you were to look at the total number of operations that happen here, it looks like we have like about 2 operations, or maybe 3 operations, because for each element we're pushing it to the first stack, we're popping it from the first stack, pushing it to the second stack, and then popping it from the second stack. So I guess actually 4 operations for every single number. But what does 4 times big O of n, or just n equal? That's still big O of n, right? That constant 4
O of n.
So it looks like
going to infinity, guys. 4 is just a constant and goes out of here.
I just realized I already showed you if we had a long sequence of pushes and then a long sequence of pops, because again, we push each element and then pop it and then push it here and then pop it. And remember, each of these operations is constant time. So even though this would be constant time, this would be constant, this would be constant, the pop itself, the first one would technically run in big O of n time because we'd have to move all of these here. Then after that, every pop would be constant time. And again, I just showed you we're only going to do it 4 times for every single number, so it's not going to be super inefficient. Now you might be thinking, what if we just had a single push and then a bunch of pops came after that? Well, that's not really possible. We can't pop if we haven't pushed anything, remember? So that's the idea here. Again, average case time complexity of push and pop is going to be constant. I want to quickly go over empty. How do you think we're going to resolve that? Because we are working with 2 stacks. We would just check if both of them are empty, we return true. If that's not the case, let's return false. What about peak? Well, remember, when we pop, we're popping from stack 2, so when we're peaking, we should just take the element without necessarily removing it, and then we can return that element. What if, though, stack 2 is actually empty? We haven't pushed anything to it yet. What if we just have 1, 2, 3, 4 in the first stack? Well, let's have an if statement in our code to check for that. If stack 2 is non-empty, return the last element from stack 2. If stack 2 is empty, return the first element from stack 1. And now that I think of it, we're technically not allowed to index a stack, so I guess probably the best way to handle this would be kind of the same way we handle the pop. So I guess, depending on the language you're using, we can do that same operation, so that's what I'll do, I guess. So instead of that whole if statement thing, let's just handle it this way. Okay, now let's code this up. Let's declare our 2 stacks. I'll call them the same thing, stack 1 and stack 2. Technically, these are arrays or dynamic arrays in Python, but we'll just be using them as a stack. So let's just keep in mind we can either push to it, we can pop from it, or we can look at the last element in the stack, the top element. By the way, if you're wondering how I figured this out, I'll keep it real with you. I actually was able to solve this problem because I had solved it before in the past. Otherwise, I don't know if I would be able to. But in pushing, let's take stack 1 and append x to it. That's the easy part. Okay, popping, this is where things get tricky. Ultimately, we want to return from stack 2. We want to take stack 2, pop the last element, and return it. And by the way, they guarantee to us that pop is only going to be called if we actually have an element in the stack. We don't have to worry about edge cases where the stack is empty. Or rather, the queue is empty, sorry about that. Same thing with peak, we can't return the front of the queue if the queue is empty, so we don't even have to worry about that. Now, it's possible, like I said, that stack 2 is actually empty. So if not stack 2, then let's take everything from stack 1 and move it to stack 2. So while stack 1 is non-empty, take to stack 2, we want to append the last element from stack 1. So pop that element. That's perfectly valid in a stack, so stack 1 dot pop. Great, we have completed pop. Like I said, this is going to be pretty similar to peak. I guess there's going to be a bit of redundant code. If you want to move it into a helper function, you can. I probably won't be doing that.
I want to see
only
the
difference
next
between
one.
peak and pop is that instead of popping the element, we just want to return it. So think of it like this: return self.stack2, the last element. In Python, I don't know if top is a method, so the way to get around that is just to return the last element, which you can just get with the -1 index. And we're allowed to do this because technically this is top. It is pretty much a real stack operation. Now, it's possible, again, that stack 2 might be empty. If that's the case, let's just take everything from stack 1 and move it to stack 2 before we execute this. So instead of writing it out, I'm just going to copy and paste it like that. Done with this, and the only thing left for us is the easy part, thankfully. So let's implement empty. We just need to check that both of the stacks are empty. So return, let's say, length of stack 1, and we're going to need length of stack 2. And we can check that they're both equal to 0, or I guess a slightly clever way to do it would be just to take the maximum of both of these and then check if that's equal to 0. Because it's not like the lengths are going to be negative. If even the maximum is equal to 0, we can assume that the other one is also equal to 0. So that's the entire code. I will admit this is a bit hard for an easy problem, at least to come up with the amortized approach. That part is definitely not easy, but you can see on the left that this works and it's pretty efficient.
Well, now I'm about to come up with the easy because I've done so much. So guys, so when we initialize it first, we want stack 1 and self does stack 2, okay? Then we gotta append to stack 1, and we're doing everything based around stack 1. If not self.stack2, meaning stack 2 doesn't exist yet, while self s1, while stack 1 exists, self.s2 append, self1 s1 pop, turning into a stack, and then we're gonna return self.s2.pop. Perfect. If not self s2, well, while self.s1, self.s2.append, self.s1.pop. Okay. Return self.s2.negative-1. Perfect, guys. Return max len self.s1 len self.s2 equals 0. There we go, guys. Nice-oo. I like it. I like it a lot. This empty one's a really cool approach. I didn't even think about it. Take the max of 2 and see if it's equal to 0. That's smart, both of them. Nice, guys. Let's do that little binary switch. Square root x. You're given a non-negative integer x, return the square root of x rounded down to the nearest integer. The return integer should be non-negative. What? Why would you... What? Wait, what? So what is this? What's the square root of 13? Oh, rounded down, so math floor. But you're supposed to use binary search. How do you use binary search for this? What?
Hey everyone, welcome back, and let's write some
Trevor,
more
want me to explain you the
Leetcode
binary
today.
search
So today
algorithm real
let's-
quick? It's pretty
No,
chill.
I'm doing homework, sorry.
Okay, it's okay. I was gonna say it's really easy to understand, but fuck me then.
Solve the problem square root of x. We're given a non-negative integer x, and we want to return the square root of x rounded down to the nearest integer. So for example, the number 4, what's the square root? It's 2. 2 squared is equal to 4. What about 8? Well, it doesn't have like an integer value square root. It's something like 2.82. You take that number and square it, you get 8. But in this case, we would want to still return the value 2 because it's the square root rounded down. So how can we solve this problem? Well, given an integer, let's say x equals 7, how do we find the square root? We know it's going to be 2 point something something, and we're going to round that down to 2. But how would we determine that? Well, the brute force would be to just iterate 4 in range, let's say starting at 1 and going all the way up until the x value, which is in this case 7. We're going to brute force this and find the square root. We know the square root is going to be less than 7 and probably greater than or equal to 1, though it probably wouldn't hurt to start at 0 because in this case our input value x could be 0 and the square root of 0 I guess is also 0. But that's a minor detail. Let's say we start at 1, we square 1. That's equal to 1. Is that the square root? Well, let's try the next value. 2. 2 squared is equal to 4. Is that the square root of 7? Well, let's keep trying. We get to 3 now. 3 squared is equal to 9. So we went too high. We are now greater than 7. So 3 is not going to be the square root because we know we're going to round down anyway. The last value that we saw that did not go over was 2. 2 squared was equal to 4. So 2 is going to be the square root of 7 rounded down. Now, the downside with this solution is that it is a brute force solution. It's actually not big O of n, even though it kind of looks like it, because we know that the loop is going to terminate before we get to n. It's going to terminate by the time we reach the value, which is the square root of n, which makes sense because let's say, in terms of n is the input value x. We know we're going to stop by the time we get to the value, which is the square root of n, because we know that value squared is going to be equal to n. So in reality, this for loop is going to run in big O of the square root of n time. But we can actually do even better than this as well, because we can use a binary search approach, which is going to be log n. Now, before I explain it, you might be wondering, how do we know that this is more efficient than the square root of n? Because it's not super obvious. Well, I won't give you like a super long mathematical proof, but intuitively, we can think about this in terms of big N values. What is the square root of n if n is equal to 1,000,000? Well, the square root of 1,000,000 is going to be 1,000. Well, what is log base 2 of 1,000,000? Well, it's going to be an integer value. I don't know the exact value, but I know it's in the magnitude of like 20 or something, maybe 21 or 19, something like that. But clearly, that's a big difference. Square root of 1,000,000 is 1,000. Log base 2 of 1,000,000 is 20. You can clearly see that log grows a lot slower, so log is going to be much more efficient if we can achieve a solution like this, which we can using binary search. We know our search space is going to be between, let's say, 0 all the way up until x. It's a range of values. We're going to calculate the midway point, so 0 plus x divided by 2 is going to give us some midway value. We're going to check m squared, is it greater than x? Because if it's greater, we know that this can't be the square root of x, and we need to now decrease our search space. So if this is true, what we would say then is we're going to cut our search space in half and now start searching between 0 and m minus 1, whatever that previous m value happened to be. And we're going to continue doing this. Suppose next time we calculate the mid value and mid squared is actually less than x. Then we would do the opposite. We would increase our search space and then search on the values on the right side of that. And we would keep doing this, but the difference here is that when our m squared value is less than x, this is going to be a candidate for our result because we basically want the largest value, the largest m value, where this is true. That's assuming, though, that the square root is going to be a non-integer value. It's also possible that the m squared value actually is equal to x. If this was the case, suppose like an example like this where 2 squared is equal to 4, if this is the case, we basically return immediately. So that's the idea of how we're going to solve this with binary search in log n time. It's going to make even more sense when I show you the code right now. So first things first, let's initialize our search space. Left is going to be set to 0, right is going to be set to x. We're also going to initialize our result. It doesn't really matter what value we give it. I'm just going to give it a 0. And then we're going to run our binary search while left is less than or equal to right. While our pointers haven't crossed each other, we're going to continue searching. You could say m is equal to left plus right divided by 2, but that could possibly overflow. A better way to do it is to say left plus the halfway distance between right minus left. So taking right minus left and dividing that by 2. This also gives us the same value as before. It's a different math equation for the same value. The only difference is that this will never overflow. It's a minor detail, but I think it's worth knowing. Next, we're going to run our equalities. So we're going to check, is m squared, you can square it like this in Python, is it greater than x? What happens if it's greater than x? Then we're going to decrease our search space. We're going to say right is equal to m minus 1. We're going to search on the left side. Else, if the opposite, if m squared is less than x, then we're going to search on the right side. We're going to say left is equal to m plus 1. But also, if this is the case, we possibly want to set our result to this value because this could be the result. This mid value could be the result, so we're going to set it like that. Now, the third case, and this might not always execute, is that m squared is equal to x. We can just use an else condition for that, and then we would want to immediately return the mid value because we found the exact square root. Otherwise, we know that the loop is eventually going to terminate, and by the time it terminates, our result will be set to basically the greatest mid value that was less than x. Well, the greatest value that we could square that is less than x, which is basically the square root rounded down. So in that case, we would want to return the result outside of the loop just like this. So now let's run the code to make sure that it works. As you can see, it does. It's pretty efficient. If this was helpful, please like and subscribe. If you're prepared for interviews, check out Neek.
What? Nah, I'm full right now. Thank you, though. Brute force solutions, very sloppy. No built-in function. They said that. Oh my golly god. Oh my golly god. Newton's method. Alright, let's try the binary search. Left, right, which is equal to 0 and x. Okay. Result is equal to 0. While left is less than or equal to right, middle is equal to left plus r minus l and then floor it by 2. Yes, I agree. That is how you do it. If m times m is greater than x, we move the right pointer equal to m minus 1. Else, if m times m less than x, l is equal to m plus 1. The result is equal to m. Guys, listen, if you see these and need help understanding it, feel free to ask in the chat. Your boy is willing to help. Looking good, binary search gang. Looking very, very good. I like it a lot. Got the binary. Let's do linked list, baby. Oh, reorder the list. Oh my. You're getting ahead of a single linked list. Guys, single linked list means one node points to the next node points to the next node, and you can only start at the head. Doubly means you can go backwards as well. But singly means it cannot. So we keep the head the same, but everything else changes. How do you do that? I don't know. LinkedIn is asking this question. Why would LinkedIn be asking this in an interview? What kind of software engineers do they got at LinkedIn?
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem reorder list. So we haven't done a linked list problem in a while, and this is a pretty common and interesting linked list problem. So we are given the head of a singly linked list, you know, where we have the first value, the next value, etc., and we want to rearrange it into this order. And a better example would be, so for example, take this linked list, and you know, we have 1, 2, 3, 4. That's a straightforward ordering. But we want to take the first value, leave it here, then take the last value, move it in the second position. Then the second value gets pushed forward, and then the third value is going to go next. And so in other words, what we want to do is, given the original list, we want to take the first value, put it in the first position, then take the last value, put it in the next position, then take another value from the beginning of the list, put it in the next position, then take another value from the end of a list, and keep doing that. So basically, we're alternating between the beginning and the end, and we're continuing to pick nodes and then building a new linked list. So just like the problem name, we're just reordering this list. We're not actually going to be creating new nodes. We just want to take each node and then put it in the correct position in the output string, and then we don't have to return anything because we're just modifying this list in place. So there are many ways to do this problem. I'm going to be focusing on the solution that we can do in linear time. Basically, n is the size of the linked list, but we're going to do this without any extra space. And it's not too difficult to do this with extra space, but without extra space, it's a little bit more tricky, but it's also pretty doable. So that's what I'm going to be focusing on. So if we were using extra space, what we actually could do is take this entire thing and put it in an array. So each node goes in the array, and what we would do is we would take the first portion, leave it as it is, and then we would take the second portion and either reverse this entire portion or just go through it in reverse order. So, you know, something like this, having one pointer at the beginning, one pointer at the end, and using that, we would build the output list where we would say, okay, the first pointer is, you know, the first position.
Too obvious of a concept.
Shift the pointers by one, and basically rinse and repeat until we've done the entire list, right? Take this, put it in the next position, take this, put it in the next position, and then, you know, if we had an array with each value in the correct position, for example, if we built an array that looked exactly like this, then of course we could take the nodes themselves and create a linked list following that exact same ordering. But we can actually do this without using an array. We can do this without using extra memory. So let me show you how to do that. So the idea is going to follow similar to what I just showed you. We want to take the beginning of the list and merge it with the second half of the list, right? So this is the first half, this is the second half. We want to merge these together with alternating values, right? So this is going to go first, and then this is going to go second. So obviously, we're not merging them from the beginning. The second list is going to be merged from the end. But if we're not putting this in an array, how exactly can we do that? Because we're going to have one pointer at the beginning of the first array. We're going to have one pointer at the end of the second. I think I said array, but what I meant is list. Obviously, we're going to have two lists. And so the first half of the list is going to be straightforward, right? We're going to take, you know, this is going to be the node that goes at the beginning. Then we're going to take this pointer, shift it to the right. So that's pretty straightforward. But since we have a pointer at the end of the second list, and you know, we take this node, we put it in the second position, right? We'll insert it somewhere in the middle over here. That's not impossible, right? We can do that pretty easily. But the problem becomes, okay, once we've inserted this node, then we want to move our pointer to this node, but the link is going the wrong way. The link is going in order, but we really want the link to be going in the opposite order, because when we traverse this second portion of the list, we're not going to be going from beginning to end. We're going to be going from end to beginning. So how can we do that without extra memory? Well, the easy way is, why not just reverse the links, right? For this entire second portion of the list, why don't we reverse every single link, and then we can do it pretty easily, right? There's no reason that we can't reverse the links. We're perfectly free to do that. So that's kind of what makes this problem a lot easier. There's going to be two phases to this algorithm mainly. We're going to take the second portion of the list, reverse it, and then we're going to take these two portions of the list and merge them together. This first, next this value, then this, right, et cetera, et cetera. The only other thing that I want to mention is when we're reversing the second half of the list, how do we know what is the second half? How do we know we've reached the second half, right? Starting from here is when we want to start reversing. How do we know once we get there? You can do it multiple ways. The easiest way is going to be a fast and slow pointer. So I'm going to have the slow pointer initially at the first and the fast pointer initially at the second node. We're going to be shifting the slow pointer by 1. We're going to be shifting the fast pointer by 2. And we're going to keep going until the fast pointer either reaches the end of the list or reaches the last value of the list. And once that is the case, we know that the slow pointer is going to be, if it's an even list, you can kind of run through it yourself and see that it does work. But if it's an even list, the slow pointer will be at the halfway point pretty much, right? It'll be at the end of the first list, right? So then what we'll do is say, okay, slow.next is going to be the beginning of the second half of the list. So that's what happens if we have an even number of nodes. What happens if we had a odd number of nodes? Let's see if the same thing works out for us. So if we had a slow pointer here and a fast pointer here, we'll shift the fast pointer by 2. It'll be over here. The slow pointer will be over here. Then we'll shift the fast pointer by 2 again. So it'll be at null over here. The slow pointer will be at this node. So I guess the question becomes, what in this case, what's the second half of the list? Because obviously we have an odd number of nodes. Well, what we're going to say is this is going to be the second half of the list. Even though it's shorter than the first half of the list, it still works for us, because what the result in this case is going to be is basically, you know, we have this second half of the list. This is the first half. We're going to take 1 at the beginning. We're going to take 5 in the next position. Then we're going to take 2 in the next position, right? We're just basically alternating. Then we're going to take 4 at the next position. And lastly, we're going to take 3 in the next position. So it does work out in this case. So you can see that, you know, finding the middle of the list is something that can be done with 2 pointers, one fast and one slow. And in terms of actually taking these lists and
they call the tortoise and hare algorithm, baby. Tortoise and hare.
Different pointers, but just to give kind of the rough idea, we're obviously going to have a pointer here, which is going to be the beginning of the first list. We're going to have a pointer here, which is we're going to call the second pointer the beginning of the second list. Obviously, the link here is going to be going the other way. What we're going to do is we're going to take, okay, this pointer dot next, right? 1 dot next is, instead of being set to this node, we're going to break this link, set it equal to the second node, which is 5. And then, of course, 5 is pointing at this node 4. So instead of having it point at 4, we want it to be pointing at this node, which was the original next node for 1. So we're going to do that. 5 is going to point at the second node, and then we're going to shift our pointers. We're going to take this pointer, set it to 2, take this pointer, set it to 4. Now, obviously, notice how we broke the link in both spots. So how are we actually going to be able to shift the pointers if we broke the link already? Well, we're going to have to save that link before we actually break it. We're basically going to have a temporary variable, which is going to point at this node, and a temporary variable that's going to point at this node before we actually break these links. I think that'll make more sense when I actually code it up, but that's basically the idea. And obviously, these 2 pointers, we're going to keep shifting them until they basically meet each other. And actually, one last thing, notice how the first list, so when we actually cut this in half, once we actually have a first half and a second half of the list, for the last node in the first half of the list, we actually want it not to be pointing at 4, but since this is going to be the last node, we want this to be pointing at null. So that's one other thing that we're going to do. So obviously, this is kind of about all the edge cases and making sure all of our pointer manipulation is going well. But once you have that down and you kind of have this main idea down, coding up isn't too difficult. That being said, we can jump into the code now. Okay, so now let's dive into the code. You can see we don't have to return anything. We just have to modify the list in place. So that's what we're going to do. And remember, the first thing we want to do is find the actual middle point of this list. So we're going to have 2 pointers, slow and fast. Slow is going to be at the head of the list, and fast is going to be head.next. We're going to keep going while fast is non-null and fast has not reached the end of the entire list. And as that's the case, we're going to basically shift each pointer. Slow is going to be shifted by 1. Fast is going to be shifted by 2. Okay, so that's great. So now we do have the beginning of the second half of the list. So we're going to have that second pointer. And remember, just like in the drawing picture, the beginning of the second half of the list is going to be the slow.next. So this is the second half of the list. But remember, now we actually have to reverse the second half of the list. Before I reverse it, I'm also going to say slow.next is going to be set to null, right? Because we're actually splitting this into 2 different lists. So that's how we're splitting it. Now we're actually going to be reversing that second half of the list. So we're going to say while second is non-null, we want to set it to the previous node. Initially, the previous node is just going to be null. So we can set that as well. I think I can actually do it on this line. Previous is also going to be set to null along with slow.next. So basically, each iteration of the loop, we're going to store a temporary variable for second.next. But before we actually shift our pointer, we're going to say second.next is going to be equal to previous, which is initially going to be null. And then, of course, we're going to update our pointer. So now previous is going to be equal to second, and second is going to be shifted to our temp, which is going to be the next node in the list. So with this loop, all we're doing is reversing the second portion of the list. Okay, so now is the part that the second half has been reversed. Now we're actually going to merge the 2 halves of the list. So the beginning of the second, right, we want to find that beginning of the second, which is going to be the previous pointer, actually, because remember, after this loop is done executing, second is going to be set to null, but previous is going to be set to whatever the last node that we looked at was, and whatever that last node is actually going to be the new head of the second half of the list, similar to what we had in the drawing picture. So that's the second half. The first half is just going to start at the head, right? So what we can say is first is going to initially be the head, second is going to be whatever happens to be in previous. And so once you have this, all we're doing now is actually going to be doing the merge for the 2 lists. And so we're going to keep going until one of the pointers is null, and we know that the second half of the list could be shorter than the first half, so we're just going to say, okay, while second is not null, let's continue to merge these lists. So first, what I'm going to say is, remember, we're going to be storing the next nodes in temporary variables because we know we're going to be breaking those links. So the first thing we're going to do is temp1 is going to be first.next because we're going to be modifying that link, and temp2 is going to be second.next because we're going to modify that link as well. So now that we save those, what we can say is, okay, first.next now is going to be reassigned to second, and second.next is going to be assigned to temp1 because we're basically inserting the second node in between first and first.next, which is what temp1 is. So we're basically inserting it between those. So that's kind of the merging operation. Now we just need to shift our pointers. So we can say, okay, first is now going to be set to temp1, second is going to be set to temp2. And we can actually put it on the same line just to make our code a little bit shorter. So that actually is the entire code. We don't have to actually return anything, like I said, and you can see that this is very efficient because we're not using any extra memory, and we're doing this in linear time. We are iterating through the list, I think, twice, but that's not too bad.
Gang.
So I hope that this was helpful.
Amazing.
If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
How did he do that? Whoa. Whoa, guys, that's amazing. There's a brute force approach we could take. Slow. We go head.next, okay. While fast and fast.next.
Hey, I'm back.
Hey, Trevor.
Rufio's probably dying soon.
No! For context, chat, Rufio's Trevor's cat. No, Trevor, no way.
He's like as old as your sister, isn't that crazy?
Really? 19?
Yeah. Yeah, somewhere around there.
That's amazing. I want to be sad when Chini dies, bruh.
I know.
Are we gonna throw one last cat party for your cat? Or you not a cat party type of family?
No, you have cat parties?
Sometimes. You don't have cat parties?
No.
Mm-hmm. That's just a little niche. No one would get it.
Equals that.
Loki, Trevor, my favorite algorithm is called the tortoise and hare algorithm. It doesn't make sense until someone explains it to you. It's really interesting. You should learn about it. It's like, what the fuck? Like, fuck.
My favorite algorithm is the sleeper fatty.
Sleeper fatty?
Yeah.
How does that work?
Like a sleeper fatty. Bro, I don't fucking get this. Quintiles.
There.
Hey everyone, welcome.
What's a segment?
Back. Let's write some more neat code today. Let's look at a sliding window problem, a hard sliding window problem, sliding window maximum. The statement is pretty straightforward actually. So we're given an array of numbers, and we also are given a number k, which is going to represent the size of our sliding window. It starts at the very left and then works its way to the right. And so since its size k, there's only going to be k input array, then the maximum windows. Why don't and see? Okay, this is a maximum, and then we just shift our window k. How many windows are we actually going to have? Let's say the entire input is length n. In that case, we're going to have roughly k times n. My better solution how to do that right now. So I'm going to show you the best solution, but one thing you have to notice first is this. So let's say this is our input array. We have 4 numbers, and our window size is going to be 3, so k equals 3. Notice how these values are in increasing order, right? 1, 2, 3, 4. Okay, so we notice that. Now, look at our first window. We have 1, 2, 3. We see that 2 is greater than 1. We see 3 is greater than 2. Now, that's good. And so we scan through every element. 1's not the max, 2's not the max, 3 is the max. So then in our output, for the first value, we're going to put a 3. Okay, that's great. Now we shift our window to the next position. So now I'm literally just going to repeat that process the brute force way. Now I'm going to check 2. Okay, now I'm going to check 3. 3 is greater. Now I'm going to check 4. 4 is the greatest. So we add 4 to our output. And so then we're done.
We
have
back
our
at it
output.
again, Chibi.
Work that we just did. As soon as
Non-stop
we
grinding.
we know 3 is greater. So we basically eliminate 2 and 3.
Your
And
boy
we
has
know- we know
Leetcode. Your boy
next
has
to
his
the
interview
window,
tomorrow.
right?
I am
1 is
locked
no longer
in.
part of our window, so we don't need to worry about 1. What about 2? Well,
I am
2 is
here.
inside of our window, right? It's at
I've
the
already
bottom.
deleted
But
League.
since we know that this
We
3
are
is
locked
greater than
in.
2 anyway, why would we ever
You're
need
so
to
loud.
look at the 2 ever again? It's
I
never
am
going to
locked
be
in,
the maximum.
Chibi.
And let me
Let's
just make it
go.
even more obvious. Let's say
Arena's
our window size
over.
is 6, and this
League's
is our window.
deleted. Your
Okay,
boy
so
is
for our first window,
locked
we have to check,
in.
okay, the 1, another one, another one, another one, another one, and then a 4. So the 4
I am
is our
so
max.
ready.
That's great, so we can save that. And then
I
we
am
shift
so
our window to
ready.
the next position and see we're repeating all that work over again. The 1, 1, 1.
Today,
As soon as we
guys,
see this 4,
we're
we
gonna
know
be
that
setting
these
up for
elements,
Monday.
As far as we're concerned, are useless to us. We never have to look at them again. They will never be the maximum inside of our window because our window is going to continue being shifted to the right position, and the 4 is still going to be in the window even after these elements have been eliminated. And so the data structure we're going to use to eliminate these values is a deck or a DQ. And I'm going to show you the algorithm. And just to repeat myself, basically what I'm saying is if we have a window and we see a value that's greater than values that are previously in our window, then we can eliminate those values from our window. And so I'm going to show you the algorithm, and what you're going to notice is that the values in our deck are always going to be decreasing order. So this is decreasing. So we know our window, our sliding window is initially size 6, right? K equals 6. So we're going to take the first one, put it in our window, the second one, put it in our window, and then just repeat that, right? We have 5 ones, we're going to add all of them, and then we get a 4. So since 4 is greater than the value at the top of our deck or at the rightmost position of our deck, what we're going to do is we're going to pop this value off. What we're going to do is pop the top of the deck, right? And now we're going to make the comparison again. We see there's still a 1, so 4 is still greater than the
And
top
don't
of our
worry,
deck, so we're
guys,
gonna
I
pop
shall be
the
here
value.
all
We're gonna
day.
pop that. We're going to pop all of them.
At least until
and
5 o'clock.
after
Then I'm
that,
going to
we're
the
gonna
gym.
add the new value
But I shall be
4.
here all day.
And so what are we going to add to the output? So we have an output array. What value are we going to add to it? Well, the leftmost value, in this case we only have one value, is going to be what we add to the output, so a 4. And so we're done with this comparison. We don't have to look at it again, and we don't even have to consider these elements anymore. And now we shift our window by 1 position, so we're introducing a new element, 5. So before we add the 5 to our deck, what do we have to do? We have to check, is 5 greater than the value at the top of our deck? It is, because the top value is a 4. So why would we ever consider the 4 as the maximum value ever again when we know there's a 5 right next to it? The answer is we don't have to, so we remove the 4 from our deck. And then we can add the 5 to the top, and then we know that there's only one value in our deck, and it's also the leftmost position. We are going to add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our deck, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our deck. But adding and removing, we know adding and removing is an O of 1 operation to our deck, and we had to do that for every single value in here potentially. But that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm going to show you one last example. And by the way, this is called, the type of problem this is called a monotonically decreasing queue. And the reason is because our queue is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of 1 time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of 1 time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. And then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add
Do
the
I
7. We
even
only wanna
need
remove
the
smaller elements if
sliding
they exist, but in
window?
this case, that's not true. So we add the 7.
Do schools still teach assembly? Oh yeah, they do. But not like as a programming language, more like how computers are, for example. I took this one class called...
and notice how these values are in
what is the class called? Let me double check. It was 280, CS 281. Let me let this load up real quick. That was the only my introductory class as well, but that's only because my professor was like a complete. He was trying to just weed out. He was trying to weed out non-CS majors, like people who didn't actually want to do CS. He like tried weeding us out. So he made us like, yo. He made us use like he had us do a week of cardiac, which is the paper computer right here. Look at this. See, there was a week where we had to use the cardiac. This shit. If you don't know how the computer works, bit by bit, byte by byte, don't even think about being a software engineer. I remember that very clearly. We had this. This was a form of assembly. But then we had this one class. Yeah, it was this one. System, I think it's this one. Drexel CS 281. There we go. Was this a 4 credit? It's one of these ones. I'll go back here. Yeah, it was this one right here. 281. We did it in open source. We did in Risk V. This right here. We did it with the open source. But it wasn't like directly assembly. It was more like learning about whatever the hell these were again. ISF shit. Whatever the hell. ISA is what it's called. We were learning about this, and there just happened to be an assembly. Like that. But we're not really taught assembly. But I'll still never forget what my professor was talking about. Here it is, guys. This is the original paper computer. This is the original computer they had with assembly. I'm telling you guys, worst thing ever. I can literally tell you exactly how it works. The first one represents the action. And then the second two spots represent the location you're going to. So let's say you start at what? Which is a good example? You start at 0, 0. You go to 0, 1. You jump here. And then whatever that action is, for example, you do that, and then you go to the next thing, next memory spot. If you don't know every single thing about the computer, if you can't build your own computer with just a bunch of wires, rocks, and cement, don't even think about it. Guys, let me tell you, he had this class was like what, 200 students. Yo, by the end, bro, we only had 100, 112. So many, over almost half the class dropped out. And you know what's really funny? Instead of taking this introductory CS 164, you could just switch over to the other one, Info 101. Easiest class of my life. I just took it because I was trying to get a minor, but yo, a data science minor. Yo, easy as shit, guys. Breeze. Slides and a quiz. Open note. Come on. That was the craziest thing ever. And mind you, only Linux as an introductory CS.
Decreasing order. We have 8, and then
learning curve was heavy for that class.
So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck.
Wait, I'm confused. If I have to go through every value, why don't I just do a simple for loop? Do I even have to follow the rules of the problem? Current max equals 0 if for single num in nums cur max equals max, and we want cur max, and then we want single num. Why can't I just do this? If I have to go through every value anyway, return cur max. As long as it works. It's a list? Oh, wait, what? Never mind, I'm dumb, bro. Oh, oh, that makes sense. This is how they stop people like me who skim. They want the max of every sliding window. That's smart. See, this is how you stop people like me. This is how you stop people like me trying to always do the bare minimum.
Hey everyone, welcome back.
So a little DQ, req.
Anyway, why would we ever need to look at the 2 ever again? It's never going to be the maximum. And let me just make it even more obvious. Let's say our window size is 6, and this is our input array.
Basically,
Okay, so
guys, on
our
a high level
is the
here,
maximum.
if you ever just want to save more space, just cache the previous ones.
Position of our comparison, we see there's still a 1, so 4 is still greater than the top of our deck. So we're gonna pop this, we're gonna pop that to outbe what we.
Alright, I got the
to our
general
deck.
gist.
So why would we ever consider deck? We're gonna add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our deck, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our deck. But adding and removing, we know adding and removing is an O of 1 operation to our deck, and we had to do that for every single value in here potentially. But that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm gonna show you one last example. And by the way, this is called, the type of problem this is called a monotonically decreasing queue. And the reason is because our queue is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of 1 time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of 1 time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist, but in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last 2 elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're gonna pop from the rightmost position in our queue. And now we are allowed to take the 9 and append it to our queue. So we add the 9 now. We know that this is the leftmost position in our queue, and we know that in this window, 9 is the maximum. So we did this correctly, right? So we can take the 9, add it to our output. So this is the result that we're looking for. And I hope this demonstrates a few of, like, when you actually run through examples, it shows you like what you need to know. It shows you why we're using this data structure, and it shows you why it's so efficient. So now with that in mind, the coding solution is not too bad. So we are gonna have an output array to put the values in. We're also, for our window, we're gonna have some pointers. So left and right pointers, these are gonna represent where our window currently is. They're both initially gonna be set to 0. And we're also gonna have a queue. In Python, we can do collections.deck. And so we're gonna run this until our right pointer is no longer in bounds. So while right is still in bounds. So we want to our queue, we want to be able to append the value, this value, right, r. And instead of doing nums of r, I'm just gonna do the index itself. So this is gonna contain indices, because we know we can take an index like r and then easily find the number that maps to by just taking nums of r, right? But before we're even allowed to append a value to our queue, we have to make sure that no smaller values exist in our queue. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're inserting, nums of r, which is the current index we're at. So while smaller values exist in our queue, we just want to pop from the queue, just remove values while that condition holds. And only after we do that are we allowed to add the new value to the queue. We also, if our window, if the left value is out of bounds, then remove the left value from the window. So if our left index, left, is currently greater than the leftmost value in our queue, then we can pop from the left of the queue. So basically, we know left and right represent our window. So if our window is if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is kind of an edge case. Since we are starting at our window being left and right both being at 0, we have to check that our our window is at least size k. So if we want to update the output, we have to make sure our window is at least size k. So that's basically what I'm doing here. And for each iteration of the loop, basically for each window, we want to append our output with the maximum. So we know the maximum is the leftmost position in our queue. And we want not the index, but we want the actual value itself. Don't forget, like me, to update your pointer. So we know right is always going to be incremented, so at the end of our loop we can increment right. Left, though, is only going to be incremented once our window is at least size k, so we're going to put that inside of this condition. And now the only thing left for us to do is return that output. And it works, and we know that this is the most efficient solution, with the time complexity being linear and the memory complexity also being linear, because we are using a data structure, our queue. So I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Interesting, guys. A very interesting approach using a queue. The brute force one's a very easy one you can think of, which is not too bad, hopefully. Use the DQ. Let's see. Output is equal to an empty list. Q is equal to DQ. Left and right start at 0. While R, the right pointer, is still less than the length of nums, the list, while Q in nums, Q -1 is less than the nums R, Q dot pop, then we take out that value and then we append that new R value. Or I guess we append that index, right? It looks like we're appending that index. If left is greater than Q dot 0, dot pop left. Actually, no, what's the, okay. Python, what is collections DQ and what does the pop do, and pop left. So I'm guessing pop pops the right side and pop left pops the left side. But listen, guys, you can only guesstimate so much. There's truth and no truths. I'll put that append. Nums Q 0. There we go. L plus equals 1. Right plus equals 1. Turn output. Bam! How's this looking? Let's go! Alright, guys, I think I understand it. Oh, D. Oh, it means double-ended Q. Okay. Forgot, guys. Q is not always double-ended. My fault. So it returns the rightmost. Pop left. Okay. Cool, guys. Today's gonna be the last brute force study day. So we low-key just gotta thug it out. For punishment, I'm thinking we do the hard ones. We were given 2 words, begin word and end word, and also a list of words, word list. All of the given words are the same length, consisting of lowercase English letters, and all are distinct. Your goal is to transform begin word into end word by following the rules. You may transform begin word to any word within word list, provided that exactly at one position the words have a different character, and the rest of the positions have the same characters. You may repeat the previous steps with the new word that you obtain, and you may do this as many times as needed. Return the minimum number of words within the transformation sequence needed to obtain the end word, or 0 if no such sequence is existing. So I want to transform cat to sag. So cat turns into bat turns into bag, and bag turns into sag. That means we can only transition 1 letter at a time, guys. Oh, so sag also needs to be in the word list. Okay. Alright, guys. An O of n squared brute force approach would be looping through the list, looking for a word that has a 1-letter transformation, take that word, and then repeat that process again. That can be done with recursion, but what's a more efficient approach at this? There's a recommended time, it says. What's a better approach to this, guys? I can't think. Or maybe we can do some sort of tree where cat's the root, bat will go on one side. And the other change word will go on the other side. But do we want the short? We want the minimum. Because then where would I attach sat? Would I attach the bat or after to sat? Because technically sat is also part of that. Let me think, guys. Maybe we can do some sort of math where we keep subtracting. See how many letters we are off from sag. So cat would be off 2 letters. Oh. Alright guys, I got no idea. What is the solution? A breath first search. A breath first search. Meet in the middle. Yeah, I'm not thinking of that. Alright. Damn, why is Google asking all these crazy ass questions?
Welcome back.
Alright guys, let's get a little analysis.
Back and let's write some more neat code today. So today let's solve word.
I am not leaving my chair, guys, until it hits 1 p.m. US ET. So I'm going to be here for at least another 16 minutes, and I will get myself a cup of coffee. But we are not leaving!
Word ladder. This is a hard problem, but I don't think it's super difficult. There's just one little thing that kind of makes it really annoying to get this to pass on Leetcode. But the idea is we're given a beginning word, and we're given an end word, and we're given a list of words.
Oh my god.
We want to create a sequence from this beginning word.
You know, you're so used to listening here him talking 2x speed. His regular voice just sounds slow. I feel bad.
To the end word, and the end word is definitely going to need to be a part of our word list, but the beginning word actually might not be a part of the word list. And so we want to create a sequence from the beginning word to the end word. That sounds pretty easy, but there's one restriction that we have to follow, and that restriction mainly is that every adjacent pair of words in that sequence can only differ by a single character, exactly one character. They have to differ by exactly one character. And so we want to find a sequence from that beginning word to the end word where every word in between is a part of the word list, and we want to return the shortest
Guys,
sequence. So
this is my
the sequence
problem.
is basically
I literally skipped that part with my brain. That would have been...
So for example, in this example down here, we can see there's a sequence from the starting word hit, and notice how this is the beginning word, so it doesn't have to be a part of our list of words, but every other word in the sequence does have to be a part of the list of words. And that includes the end word, so cog does have to be a part of our list of words. And so in this example, the shortest sequence is of length 5 because it has 5 different words in it. Now, the convenient thing for us is that every single word, including the beginning, end word, and every word in the list is going to be guaranteed to be the exact same length. In this case, every word has 3 characters in it. So it's pretty easy to take 2 words and figure out what's the difference in characters between them, right? We can just compare character by character and see that there's 1 character difference. Therefore, we could form a path between these 2 words, right? And each edge between these words, let's say log and cog, is going to be bidirectional, right? We could go from log to cog, or we could go the other direction, right? So this is starting to look like a bit of a graph problem, right? We want to find the shortest path from the beginning node hit all the way to the end node cog, and the way the edges are going to work, so hit could be connected to any of the words in this word list where it has a single character difference. So let's think about this. So hit, which one of these words could it be connected to? Is there a single character difference between hit and hot? Yes, that's the case. So hit and hot are going to be connected in this problem. What about dot? Nope, it takes 2 character difference between hit. What about dog? Again, 2 character difference. Lot, again, 2 character difference. Same with log and same with cog. But hot could be connected to some of these characters or some of these words, right? So we're realizing that building a graph like this with all the edges,
was I right?
between the words is going to be very helpful for us.
I was right.
And there's
I
a
just
naive
didn't...
way to create this adjacency list, which is going to basically be a
I
nested
just
loop
think
on
the
the entire list of
I think my
words, which let's say
solution was
ends up
trying
being
for the
n
most
squared, where n is the
efficient.
number of words. And let's say the length of each word, which is always going to be the same, is m, because we're going to need to compare
I
character
just
by
have to
character between
keep
the words. So creating
appending
an
to
adjacency is
every
going to be something
single
like n squared
value.
times m. But, and you might think that that's good enough. Unfortunately, this won't pass on Leetcode, and I really think that's kind of stupid that it does that. The main thing to notice to build the adjacency list faster is to look at the constraints. They tell us that the length of the list of words, in our case that's n, so it's going to be n squared, right, is going to be less than or equal to 5,000, whereas the length of the word itself is going to be less than or equal to 10. So there's actually a way where we can change this time complexity to at least generate that adjacency list to something like n times m squared, because the m is going to be smaller than the n, so we can actually make it kind of like this. But I'm pretty sure that the overall time complexity, because after we actually create this graph, we're going to run a breadth first search algorithm to find the shortest path. We could do it with DFS, but usually to find the shortest path, breadth first search is much more efficient. And I'm pretty sure, even in this case, the breadth first search solution is going to be n squared, because this is going to be the number of edges we could potentially have, right? Because that's how many words we have. We could have n squared edges, and we're also going to have to compare words. So on each operation, when we're traversing the graph, it's going to be multiplied by the length of the word. So the overall time complexity for the BFS is still going to be n squared, which is, pretty much this. So you might think, well, then why isn't it passing on Leetcode? And that's a good question. I think in general, though, doing it like this is going to be faster. We use this to generate our adjacency list, and then we do a BFS with this time complexity. And basically, there's kind of a small trick that I'm going to show you, which will get it to pass on Leetcode. So like I said, the first part is building an adjacency list, and the naive way would be to go through every word hot, compare it with every other word. That's going to be n squared, and then the length of the word, which is m. But there's a little bit of a trick. So how about we do it a different way, right? We know that for any word, we want at most 1 character difference, right? So let's take a look at hot, our first word, and let's take a look at every pattern it could fall into if we change 1 character at most. If we change the first character to any other character, we could transform this into star for the wild card, and then O-T, right? We change the first character. We could also transform it into H, change the middle character, star, and then T, right? And then also to a third word, H-O, and the last character is going to be a star, right? So these are the 3 patterns that hot fits into. And now let's take a look at a different word, dot. And let's quickly do the same thing for this. So the first pattern will be star OT, next D star T, lastly D O star. So notice how, okay, these two patterns between the words are different. These two patterns between the words are different, but the first pattern for each word is the exact same. Since these both of these words, hot and dot, have the same pattern, when we remove the first character, that means that they have a one character difference between these words. And that makes sense, right? If we change the first character from here to a D, or change the first character from here to an H, these two words will be the same. That means they have a one character difference. So using this idea, we are going to create an adjacency list where the key of the adjacency list is going to be the pattern. By pattern, I mean one of these wildcard type strings, and the value of this adjacency list, in our case, it's going to be a hash map or a dictionary. So each pattern is going to be mapped to a list of words. So each pattern to a list of words. So for example, if we take the pattern star OT, we'll have a corresponding list of words for all words that fit this pattern, right? So far we found hot fits this pattern. We also found that dot fits this pattern. And by just looking at our list, we can see that lot is also going to fit this pattern. So we have 3 words that fit this pattern. So if we wanted all the neighbors of hot in our adjacency list, how would we find them, right? Because the key, it's not like hot is the key of this adjacency list. So to find all the neighbors of hot, what we have to do is first for hot, find all of its patterns, right? The first pattern, star OT, we'll go to that star and say, okay, these are all the neighbors of hot. These are all the neighbors in the graph. Of course, we can't include itself. So we'd say, okay, dot and lot are going to be the neighbors of hot. But we also know that hot can have a couple other patterns that it fits into. H star T. Are there any other words in our list that match this pattern? Well, hit is going to match that, right? Hit is going to match the pattern H star T. So in that list, we would have hot and hit. So that's how we get another neighbor for hot. And lastly, we'd see, are there any other words that fit this pattern, HO star? In our list, you can tell that I don't think any other words are going to fit that pattern. Only hot itself fits that pattern, so it doesn't have any additional neighbors. So all the neighbors of hot are going to be dot, lot, and hit from up above here. And so how are we finding the neighbors? So basically, what's the computation of what I just did? It's going to be, since to find all the neighbors, we're going to have to go from hot, consider, okay, if we remove this character, remove this character, remove this character. So basically, we're going through every word in our list, which is N, and then we're going through every single character that we remove, which is M, right? So that's how many possible different patterns we can have in total. And then to actually add each word to the list is going to be another M. So that's kind of how you can get the complexity N times M squared to at least generate the adjacency list. Now let's assume we have that adjacency list and we have a graph. Then the algorithm is actually pretty straightforward. It's just going to be a basic BFS search. So this is something like how our graph is going to look like. We know that the beginning word is hit, the destination word, the end word is cog. So we want to find the shortest path from here all the way to here. So we know that a good way to find a shortest path is a BFS search. So from our first initial spot, we're going to look at all neighbors that it has. From the picture, it's pretty obvious. Hot is the only neighbor. So far we have a path of length 2 because we're counting the number of words. That is what determines the length of the path. And of course, it's not going to be this simple to get the neighbors because we know that our adjacency list is a little bit more complicated. And again, from hot, we're going to go to its 2 neighbors, and we're never going to revisit the same neighbor twice, but we are going to potentially have to go along each edge at least once. We're also not going to go along the same edge twice, but the number of edges I'm pretty sure could be the number of words N squared. And for each neighbor, to find each neighbor, we're going to have to do an M operation where M is the length of a particular word, which is where I'm getting this time complexity N squared times M. I'm pretty sure Leetcode has the wrong time complexity for this. Somebody can correct me if I'm wrong though, because for a graph with N nodes, the maximum number of edges could be N squared. And again, from here, so we don't want to, even though there's an edge between these 2 nodes, we don't want to go along that edge because that's going to be revisiting the same nodes twice. So now we're going to go along our next layer. So from dot, we can reach dog, and from lot, we can reach log. Now there's just one last unvisited node. Both of these log could visit it or dog could visit it, but at the end, we're going to have a single another node. So what was the path? So we had 1 word, 2 word, 3, 4, 5. It took us 5 layers of our BFS to reach this. So we're going to say that our result is 5. And when you look at the output, that's exactly what they had as well. So with that being said, we can jump into the code now. So now let's get into the code. And like I mentioned, we want to make sure that the end word is actually in the word list because that's a requirement. If it's not, then we have to return 0 because that's what we want to return if there doesn't exist a path from the beginning word to the end word. We're going to have a list of neighbors. This is going to be our adjacency list. And this is the first time I'm actually going to do collections.default dict. I usually avoid doing this. I actually manually create the dictionary, but in this case, it's going to be helpful to do this. Basically, this is a dictionary where if we're inserting a new value for the first time, the default value is going to be an empty list. Also to our word list, I'm going to go ahead and append the beginning word because it's not a part of the word list initially. So begin word. Now let's actually build the adjacency list. So first, let's go through every single word in this word list. And now for each word, we want to find every possible pattern for this word. So I'm going to use a pointer J just to go through every single position of this word. Of course, we know every word is going to be the exact same length. And for each position of this word, I want to replace a character with the wildcard character. So I'm going to transform this string word into a pattern string where we're going to take the first J characters. Initially, J is going to be 0, so we're going to take that. We're going to replace the Jth character, the 0th character, with a star. And then we're going to get the remaining characters skipping the Jth character, so J plus 1 to the end of the string. So we're just going to go through every position, replacing a character with a star. And then for this pattern, we're going to say, okay, in our neighbor list, all the strings that fall into this pattern. So for this pattern, we want to append the current word. We want to say this word is a part of this pattern, and that's going to help us traverse the graph later on. And of course, we're going to do that for every single word in the entire list, and we're going to do it. We're going to have that star go in every position of the word. Next, let's do our BFS. There's a couple data structures we're going to need. We don't want to revisit the same position twice, so we're going to have a set and make sure we don't do that. We know we're going to start at the beginning word, so let's add beginning word to the set. And we also need a queue, and we're going to similarly add the beginning word to this queue, and we're just going to continue popping. We're going to go layer by layer until we get to the end word. And initially, our result or our length of the path is going to be 1 because we have at least 1 word. The length is going to be the number of words along the path. And now we're going to continue going while the queue is non-empty. If we find the word, we're going to end up returning the result. If we don't find the word, when the loop exits, we're going to end up returning 0. So let's do that. And so we want to go through the entire layer, and then we want to increment our result by 1. So I'm going to increment result by 1 after we go through the entire layer, and then we're going to continue going layer by layer until our queue happens to be empty. So let's go through whatever the length of the queue currently is. Let's go through every single node and pop that node. So queue.pop left. And when we pop, we're going to be getting a word that we ended up adding. If this word equals the end word, then we can return the length of the path, aka the result. If it's not the end word, then we're going to go ahead and take the neighbors of this word and add them to the queue. How can we get the neighbors of this word? Well, first we have to see all the patterns that this word falls into, and then we have to get all the other words that fall into the exact same pattern because that's the most efficient way to get the neighbors. So first let's go through for every J in range of the length of this word so that we can replace each character with the wildcard character. So let's transform this word into the pattern. So basically the exact same thing that we just did up above, I'll literally just copy and paste it. So this word could be replaced with the pattern, right? And now using this pattern, we can get all the neighbors of this word. So let's go through for neighbor word in neighbors of this pattern. Now, of course, we might be able to get that same word, but the reason we're not going to get the same word is we're going to check if this neighbor word is not visited. So if neighbor word not in visit, that's when we're going to be processing that word. So we definitely won't be looking at the same word twice. So if this neighbor word has not been visited, we can of course add it to visit, and we can add it to the queue. So queue.append neighbor word. For some reason up above, I said if end word is in the word list. I meant to say if it's not in the word list. In that case, we're going to return 0. But other than that, the code is correct. You can see that it's pretty efficient. That's because we kind of used this trick to find the adjacency list. I feel like this shouldn't be required to pass this problem, though. I think that's kind of dumb on Leetcode's part, but for some reason it is. But once you kind of know that trick, this problem basically just reduces to a breadth first search. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.
Nested statements too advanced for me. Trust me. I don't even know what bro wrote. It just went in and out the other. But he's saying there's a more efficient one he wrote. Interesting. Kind of numerical. It was pretty efficient. I will have to give it to him. That was beautiful. It was beautiful. Alright. So here it is. So, if n word not in word list returns 0, that was given by the problem. The neighbor is the collection's default dict list. Now, let me just be for real. I don't know how this works. Show me how default dict works. What does it look like if I pass list in and, for example, int or string? Bam. This is how you learn, guys. Asking questions. Word list dot append so he appends the begin word into the word list we were given. For word in word list, okay. For j in range length of word. So we have this individual word. We now have an index value for every word. Something something result. Lol this, lol that. We make a pattern for word j plus star. Star represents a wild card. Plus word j plus 1. Okay, guys. So this is the star pattern he was talking about earlier. And then this is where we set that pattern as the key. And we append the word after, okay? Default dict is just like normal Python dict, but with a default value for missing keys. When you access a key that doesn't exist, instead of throwing key error, it creates the key automatically. Default dict. Since A and B didn't exist before, since you passed list, each missing key starts an empty list. Oh. Okay. Oh, that's pretty cool. Let me ask chat to explain it with a normal dictionary. So I'll get a key error if I try to append. Okay, cool. This is good to know, guys. Good to know. I like it. I like it a lot. I'm gonna give you a +1 for being interesting about it. So it appends the pattern. Visit equals the set of begin word. So it takes every unique value of that, and then it takes a queue, a double-ended queue, with begin word. Okay. The result is equal to 1 while queue exists for I in range length of queue. So we have a bunch of index values. Word is equal queue pop left. So we're taking the first value. If the word is equal to n word, return result. For j in range length word, pattern equals word j plus star plus word j plus 1. Okay. Now go over every variation of list slicing in Python. Bam, there we go. We got that. I still need to work on my list slicing. For neighbor word, not in visit, visit dot add nay word. You know what? Now that you said that, I hear it. I hear it now. Now that I'm saying it, I hear it. Chibi. There we go. Hopefully I didn't type anything wrong here. Oh yeah, probably not right yet. I forgot my previous for loop. Broke my mouse still, y'all. Still need the new mouse. But what? Slight typos, guys. Slight typos. Holy. Finally. Finally. Alright, guys. Give me like 5. Chill. Here, I was coming back with some products. Gran Turismo. I used to play this game, but not the boomer variation. What kind of graphics are these? What year was this made? 2004? Oh my. You're for your thank you. Listen guys, I brought banana bread with some whipped cream back on top. I'm gonna munch on it while I complain about how hard my life is. Even though I have the opportunity to study. Look at that. Look at that guys. See the way I did that wording? Alright, let's is there anything with just matrices? Is it this one? Which one's the matrix ones? There we go. So let's do this one, guys. This is my weakest one. I just figured this out. Let me
Hey
eat
everyone,
and enjoy my
welcome
stuff.
back and let's write some more neat code today. So today let's solve another graph problem, walls and gates. So we're given an m by n grid where each position could have 3 possible values. A -1, which represents a wall, aka an obstacle that we're not allowed to visit. We're not allowed to visit these walls. A 0, which identifies a gate, so this is an example of a gate in this case.
Oh my.
And the third value is infinity, which basically represents an empty room. And basically for every single empty room, aka every position that's marked as infinity initially, we want to identify what's the nearest gate to that room, and then we want to take the distance from that room to the nearest gate and then replace that infinite value with it. So, and if it is impossible, basically if an empty position cannot reach a gate in our graph, then basically we're going to leave that position as infinity. So for example, let's take a look at this example. The easiest one over here, right? How far away is this empty room from a gate? Well, it can go in 2 directions. It can go down, which is an obstacle, so we're not allowed to travel in that way. We can't go up or to the right, those are out of bounds, but we can go to the left, and of course, right next to it happens to be a gate, so what we're going to place here is a 1, meaning this is 1 position away from a gate. And similarly, this one, how far away is this from a gate? Well, 1, 2, 3 positions right from a gate. So we could put a 3 here, we could put a 2 here, and a 1 here. What about this one? We could go 1, 2, 3. So it's 3 positions from this gate, but it happens to be that there's a closer gate if we go to the right and then we go up, right? So the closer gate is actually 2 places away, so we're going to put 2 in this position. And now what happens if there was a gate over here? What would we mark these 2 as? Well, basically they start out as infinity, and we would leave these 2 positions as infinity. So any positions that cannot visit a gate are going to be remaining as infinity. So the first idea that you might have for this problem is basically for every position we want to know what's the closest gate. Why can't we just run a DFS, right? Basically a DFS until we reach the gate, or we reach as many positions as we can. We return what was the closest gate to that position, right? And then do that for every single position in the entire grid. Now what's the time complexity going to be of that? Well, a DFS is going to basically be the size of the grid, and we're going to do that for every single position in the grid. So basically it's going to be something like m by n squared. So the question is, can we do better than this big O time complexity? Well, let's try out a BFS solution, right? We tried DFS. Let's try out breadth first search and see what that leads to us. Let's say we started our BFS at some arbitrary position like this one. Is it possible that we can eliminate repeated breadth if we do that?
coffee's
Well,
horrendous.
we're going to start here and then visit in all 4 directions.
Not put too
and
much
see
coconut sugar in there.
What's the closest gate that we can get to. So starting here, we have a distance of 0. It takes us a distance of 1 to get to these positions, and then finally we can get a distance of 2 to get this position, right? But since we don't want to revisit the same node twice, the same position twice, we're gonna do exactly that. Once we get to a position, we're gonna leave it as visited. So if we go,
I'm already
from here
thinking
to
about
here, it takes us
League.
2 positions. So then we can say, okay, for this position it took us 2. But when we go up, right, we get to this position, we can't really go in any other direction. So basically this is going to be remaining as a dead end. We're never going to get a distance in this position, right? Because we don't want to revisit the same position twice. We can't go back in the direction that we came from. So a BFS solution starting from the rooms is not going to work if we want to get an actual O of m by n solution. It's not going to work if we do it from the rooms. But let's reverse our thinking a bit.
Do you know what the worst part is, GB? I got like this beefy ass PC. It takes like 10 minutes to reinstall it. So the urge to fight it is always just there.
Solution from the gates. So for example, from this gate we can say, okay, let's mark all adjacent rooms basically as saying, okay, all of the adjacent rooms are one distance away from this gate. And then let's continue that. So from this room doesn't have any other rooms adjacent to, but this room does. So we can say, okay, for this room it's 2, and this
you don't know how many times I relapsed. You don't want to know how many times I relapsed.
This gate, and we continue, right? We say, okay, this room is 3, and continue from here. This room is 4, and from here, similarly, right? We'd say, okay, this is 3. This is 4, and this is 4, right? But is that actually true? Is this room 4 positions away? Well, we forgot about this gate, right? So a better way of doing this would be to simultaneously do a BFS from both gates at the exact same time. So in that case, if we ever reach a position, so let's see what happens when we do a BFS simultaneously. So from here we're gonna say this is 1, these 2 are 1 position, and this is also 1 position. Now from all of our ones, we're gonna continue.
My body's
the BFS,
already coughing
right?
up
So from this one
from
we'll
not
say
playing League.
these rooms are 2 away. From this one we'll say this room is 2 away, right? Now from this room, right, this is 2 away. We're not going to go to this position and say that it's 3 positions away, because this has already been visited. We've already found the minimum distance.
We're caching results already.
At BFS, right? So every time we expand one layer, we're saying, okay, first let's find all the rooms 1 distance away from a gate. Next, let's find all the rooms 2 distance away from the gate, and 3, and we keep doing that until every single position in our grid has already been visited, or we basically cannot continue. And we know BFS solutions are implemented with a queue, so once our queue is empty, that's how we know we can stop. So let's just continue a little bit more. So from this 2, the only unvisited neighbor is this one, so this is 3 positions away. This one is also here. So now we're going to do a BFS from the remaining 3s. We can see only this 3 actually has a neighbor, so we'll say this one is going to be 4. And take a look at the actual output that they built. Our solution exactly matches what they did, and we didn't have to revisit the same node twice. All we had to do was initialize our queue with the 2
All right, guys.
initial positions for the gates, and then
You
expanding
know, let's
outwardly,
take
basically
after this,
incrementing
guys.
the
Let's take a
distance every time we
break.
complete a
Let's
full
apply
layer
that
of our
1,000
BFS,
jobs or
traversal,
some
and
shit.
that
I
actually
don't
led to us
even
having
know.
a time complexity of m
Tired
by n.
of
We're also
this
going to
shit
have
right
that
now.
as the memory complexity because we're going to have a set to make sure we don't visit the same position twice. But once you kind of know that this is going to be a BFS from multiple sources at the same time, implementing the code is pretty straightforward if you know how to do BFS. So first things first, let's get the dimensions of our grid, so the number of rows and the number of columns. I usually like to do this at the beginning. So, and we're also going to have a visit set that is going to make sure that we don't visit the same position multiple times. And we're also going to have a queue, which initially lets set to being empty, but we're going to initialize that with the gates first of all, right? So now let's go through every single position and actually initialize our queue, right? We know we're just going to do that with the gates, so we're going to have to go through the entire grid, over the entire grid. And even though we're doing this, it's not actually going to change the overall time complexity. So we're going to go through every position. If rooms at this position is equal to a gate, meaning it's equal to a 0, then we're going to add it to our queue. So we're going to say queue.append this position, and let's make sure to add it to the visit set because we don't want to have to visit the same position twice. We're doing our BFS, so initially the distance is going to be 0 because we're going to be popping the actual gates first of all. So we're going to say
We're
while
still
queue is
here.
now empty, we're going to go through every single position in the queue currently, right? Basically this layer of the queue, and so we're going to be popping from the queue. So pop left from this queue. We're going to get the coordinates of the gates that we
I
initially
have the
added. That's gonna be
opportunity
the first layer.
to
The
do
first layer
this.
we're going to be popping are the gates that we just added, right? So for each gate, we're basically going to say, okay, let's change this gate to being the current distance. So since the
How
current
does
distance is
some
initially
people
0, and
just
remember the
lock
gates start
in
out as
for
having
like
a value of
20
0, we're not actually going to be
hours?
modifying the
This is
value of the gates. But the reason I'm putting this line here is because after we pop the gate layer, the next layer that we're going to add to our queue is going to be all the rooms that are one distance away. So after this for loop, let's make sure that we remember to increment our distance by 1 every time we complete a full layer of the queue. And so basically for this room, let's just go ahead and add room. We're going to add every single neighbor of this room. And you can see I haven't actually defined that function yet, so let's do that up above once I actually write this out. So basically what I'm doing is going to be adding all 4 adjacent rooms to the queue. And we obviously know that some of these rooms might be out of bounds, some of them might have already been visited. That's why I'm going to put this in a helper function to basically abstract some of that logic for us. So let's define the function up above over here. So add room, we're just going to pass in a couple coordinates. So basically if this row is less than 0, or if the row is out of bounds, meaning it's too big, meaning it's equal to the number of rows, or the exact same thing for column, if column is less than 0, or column is too big, or if this position, row column, has already been visited, or one last condition, basically if this room is a wall or an obstacle, right? Because remember, not every position in our graph is a empty room. It's possible it could be a obstacle, meaning it's equal to -1. So if any of these above conditions is true, we're going to immediately return because this is an invalid room, so we're not going to actually add it to the queue or the visit set. But if it's not invalid, that's when we can go ahead and say, okay, visit.add to the hash set, and go ahead and queue.append to the hash set as well. Right, so basically you can see why I'm putting this stuff inside of a helper function, because we don't want to have to call that 4 times. And I don't really want to put a loop in here because I just think it's kind of messy. I'd rather just write it out like this. But so with all of that done, we can see that we have added the rooms. We're making sure to increment the distance every time we complete a layer. And we're basically going through rooms, labeling what's the minimum distance from that room to a gate. Once we're done with that, we don't actually have to return anything because we just have to modify the rooms to the array in place. So this is all the code that we're actually going to have to write. So you can see that this solution is efficient. We're basically visiting the entire grid a couple times, I think 2 or 3 times, because of course we have this initial loop and then we actually have to run our BFS solution, but it's still a linear time solution with respect to the size of the input array. So I hope that this was helpful. If it was, please like and subscribe. I support the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
I'll never forget, guys, when I used to work at BlackRock. I lost my personality. I had nothing to do. They had people ask me, what did you do outside of work? I said, I don't know. I'm never working there again. Holy crap. Leetcode is getting so bad, I'm reminiscing about my bad days. This is bad, guys. Oh, this is pretty cool, guys, that to get the number of columns, you just want the length of one of the grids. That's interesting. Visit is equal to a set. Queue is a double-ended queue. I'll never forget. Add cell. Row column. If min of the row / column is less than 0, or row is equal to rows, or col is equal to cols, or r comma c in visit, or grid rc equals -1. Oh, the pain. Return nothing. Else visit dot add. Not a pen. R comma C. Okay. Range rows for C and range calls. Oh. If grid C are row then columns. Visit.add RC. Oh my. Distance is equal to 0 while Q While Q, there is a double-ended Q for I in range. Len of QQ R comma C equals Q dot pop left. Grid RC dist add cell R plus 1 C add cell R minus 1 C add cell R C plus 1 add cell R C minus 1. Oh my. This plus equals 1. I remember returning. Oh. Run! Let's go! Look at that. Alright guys, I'm tired of this shit. Start applying at some jobs. I need a job. Just gonna play some music. I need some music, guys. Something to inspire me. There we go. I want to be a hero. 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 Let's go for it, guys.
Hey everyone, welcome back, and let's write some more Leetcode. So today we're going to be solving Leetcode 11, container with most water. So we're given an array of heights. So this is a height 1, this is a height 8, 6, so on and so on. And using these heights, we want to see what's the biggest area we can form with a container that has a left height and a right height. So in this example, you can see that if we take this one with a height of 8 and this one with a height of 7, we can create an area. Let's see how wide this is. Like 1, 2, 3, 1, 2, 3, 7 wide and 7 tall. So that's 7 by 7, and the area is going to be 49. And they tell us that much in the explanation. So since we're given a list of heights and we want to maximize the area, we can potentially just take every single combination, right? So check every left pointer and every right pointer. So my first thought with this is, what's the brute force way? What's the easiest way to solve this problem? Well, let's just try every single combination of left and right. Let's just try every single possible container we can make and see if it works. So let's say this is our left and this is our right. What's the max area we can make with this? Well, let's fill it up to 1. And if we keep filling it up with water, notice how it's going to spill to the left, right? So this left pointer is our bottleneck, right? We have a height of 1 and we have a height of 7. The minimum one is 1, so we can't fill it up any higher. The width of this is also 1, so we get an area of 1 by 1 with water. And of course, if this one remains our left pointer, we can try this one as our right pointer. And in this case, the width is going to be 2. So area, that's going to be, we move set here, and then we're going to find our result, right? It's going to be 7 by 7. That's the biggest area we can do. And since we're checking every single combination, we know we're eventually going to find the correct solution. The only downside is that this algorithm is big O of n squared. Now, is that good enough? I guess it depends on your interviewer. And let me just quickly code up the solution for that. So this is the brute force of this. So I'll make a pointer. Okay, so let's do that. So we're going to find that, because no matter how tall no matter how tall one of the heights is, right, we could extend this to 1,000,000, but look how small this one is. It's just too small. The water's going to spill out. So we care, no matter how tall our right, no matter how tall one, remember we're minus left multiplied by the height. Now, how do we find the height? So how do we find the height? Remember, we're focusing on what the bottleneck is, and by bottleneck, in this case, we mean the minimum height, because no matter how tall one of the heights is, right, we could extend this to 1,000,000, but look how small this one is. It's just too small. The water's going to spill out. So we care about the minimum height of the left and right pointer. So let's get that minimum. So minimum of height of left and minimum of height of right. So now that we've computed the area, remember we want the max area, so we can set our result equal to the max of itself and the area that we just computed. So every time we compute an area the max, we're going to update our result. And now all we need to do is return that result that we computed. Let's see if it works. Unfortunately, it doesn't work. We got time limit exceeded, so now we need to figure out how we can make this a little bit better. Can we get a linear time solution? So now let's take a look at the linear time solution, the one that will actually work in Leetcode. So remember how we said that the minimum height is our limiting factor. We really don't want small heights. So let's see if we can try a 2-pointer technique. Now, I'm going to initialize the left pointer all the way at the left, and I'm going to initialize the right pointer all the way at the right. Why? Because we want to maximize the area. So why would I initialize them because we want the width to be as big as possible. Because if this left height is super tall and this right height is super tall, then we've instantly found our result. But of course, in this case, that doesn't work. We get an area of 1 by 8, I think. So that's obviously not the result. So what do? How do we update our left and right pointers? So the first area that we computed was an 8, which is our max, because our initial max, because this is basically the maximum so far. So now how are we going to update our pointer? Well, we're going to look at what's the minimum height. This one has a height of 1, this one has a height of 7. So why would I shift my right pointer when it has a height of 7, when I could instead shift my left pointer, which has a height of 1, and potentially increase it? So now left is over here, and we have a height of 8. And lucky for us, we've basically found our solution, but I'm just going to keep going with the algorithm just to kind of show you how it works. So now we have an area of 7 by 7, which we know is 49. So our max area gets updated. Our max is no longer 8, it's 49, which we know is the correct solution. Next, I'm going to take the minimum of 8 and 7. 7 is smaller, so we're going to shift our right by 3. Still not left, but 4. Too small. That's a little, it's going to be work on the 0, and if that's what the other condition, then either 1. Notice how both of these are doing the same thing. So I'm just going to condense this. I'm just going to get rid of these 2 lines of code. Now all we need to do is return the maximum that we computed. Let's see if it actually works this time. Okay, of course I had a typo. So I had a S at the end of heights. Let's run it one more time, and this time it'll work. So this is the actual linear time solution.